Hello YouTube, it's me Blacklemore back at it again with another Shadertoy tutorial. This time I'm going to show you my trick to making these perfect glitchless pistons in the shader. I'm going to assume that you are already familiar with sine distance functions and remarching in general, and I'm just going to walk you through how to define a sine distance function like this one. So in order to explain it better, we're going to jump down to 2 dimensions first. So here we're going to define a 2-dimensional sine distance function of a bunch of pistons moving independently. So this is a visualizer of a 2-dimensional sine distance function. The orange parts are positive values and the blue parts are negative values. And as the color gets darker, it approaches 0, where once it's black, it's the surface. And then further from there, it becomes more and more lighter again as it goes negative. I can also click anywhere and see a visualization of the distance at that point I clicked. So here we draw a circle with the radius of the distance, and we can see that the circle doesn't intersect with the surface, and in fact touches it, and also doesn't underestimate anywhere. So this sine distance function is exact. So this object here is defined by this piston function, which I've just highlighted, and it takes in a position, which is the actual point on screen, the width and the height of the pistons. So if I, down here in my Sine function, if I increase the width, say to 5, my piston gets wider. And if I increase the height, say I put it to 5, then the piston goes up. So the first thing we're going to do is do domain repetition so that we have a bunch of these in a row. So the way we can do that is by taking the x value of the p coordinate and taking the fraction of that using the frac function. I think it's fract. Yeah, that's fract. And then subtract by 0.5. So we need to subtract by 0.5 because fract is going to range from 0 to 1. And we want this to be centered so that it goes from negative 0.5 to 0.5. So when we run this, we're going to have a bunch of pistons repeated in a row. And then what we might want to do now is make them move up and down. So what we're going to do is say, height is equal to, actually, in fact, I should probably define this further down here. That's going to be more readable. So we're going to define the height as, say, the sine of I time. And I time is just, actually, I should press play over here. I time is just the current time that the shader is running at. And we're also going to multiply this by 2, so we've got a big range. So once I do this, all the pistons are moving in the same sort of in lockstep with each other. And that's because with domain repetition, we just repeat the object multiple times, and we have no say over like each individual repetition. So in order to change the height for each individual cell, we need to get that cell. So in order to do that, we define a new floating point value called center. And this is going to be the center point, or the x position of the center point of the cell for each individual cell. And to do that, we take the floor value of p.x and we add 0.5. And that's because we did this 0.5 offset down here. We have to offset in the opposite direction to get the center point over here. So when I run this, we don't see anything yet because we haven't incorporated center into our height. But if I add that here, we should see different positions for each cell. So this looks okay. Unfortunately, the sine distance function is no longer accurate. So if I pause here, if I check the sine distance function near the top of each piston, it seems correct, but the further I get away from the piston, it gets more and more incorrect. So over here, where I've put my cursor, we can see that the distance estimate is intersecting with a lot of these pistons over here. So if we were to remarch this, suppose that our ray is going in this direction. If we were to remarch this, and the current point was here, it would just jump right through this piston and we'd get glitches. So this is the source of a lot of glitches when you're doing domain repetition, where you take the actual sort of ID of the domain and then modify something about the sine distance function in that domain. So how do we fix this? One immediate thing that might come to mind is, what if instead of taking just the height of the current piston for the current cell, what if we loop over neighboring cells and take the minimum of those pistons? We basically take the union, because in SDF world, when you take the minimum of 2 sine distance functions, it's equivalent to taking the union of the 2 objects that they represent. If we take the union of neighboring cells, maybe that'll give us a better distance estimate. So let's implement that. Okay, so I've implemented this. Essentially, we start with a very large distance value, and we just iterate over the neighbors. So first we start at the previous one, then it goes to the current one, and then the next one, and we get the height for that cell, the piston SDF for that cell, and we take the minimum of the current distance and that. So it basically takes the union of all three objects. And this is a lot better, so I'm going to pause this here. So if I put my cursor here, the SDF is really good here, actually, because it touches, even though this point is sort of on the boundary of this cell and this cell, it knows that this cell is over there somehow. However, if I go up higher over here, the SDF breaks down again. So in this point specifically, we see that we have that same problem where the distance will cause a ray going in this direction to jump directly through this piston. And that causes, of course, glitches. So maybe what we could do is increase the number of loops. So what if we say go to -2 and 2? So in this case, we are asking not just for the immediate neighbors, but also their neighbors as well. So if I run this, oh, wrong run button, that run button, it gets way better. So up here, the distance function is really good because even though this is on the boundary of these two cells, it knows about these cells over here. Unfortunately, as we go into higher and higher dimensions, this becomes intractable because not only does this have to be a for loop inside of our sine distance function, which is always a bad sign, this has to be a nested loop. So we need to have a better way. So in order to explain this next part, I'm going to have to explain you of a strange statement. And the statement is basically, in normal domain repetition, the objects assume that its neighbors are the same as itself. So what do I mean by that? So suppose we didn't change the height based on the position. What if all these objects have the same height? So if I change this to 0, so the height is 0, and we're still looping across the neighbors, this just looks like our original example, where all the objects have the same height. So how is this significant? What I argue is that whenever we do domain repetition, we're implicitly assuming that the neighbors are the same object. And here, when we actually explicitly do that, nothing has changed. The sine distance function is the same as if we just returned this value. So if I copy this over here, and if I just return the object, so this sine distance function, where I just return the domain repeated object, is indistinguishable from this more complicated version where I loop through every single neighbor and say, okay, what's your height, what's your height, what's your height, and they all have the same height. So if I run this, same thing. So my argument is that when we do domain repetition, we're doing this implicit assumption that the neighbors are the same height. So the question is now, can we make a different assumption? What if instead of assuming that the neighbor is the same height, what if we assume that it is the maximum height these objects can take? What if we assume that it is the worst case scenario? Because the worst case scenario is an object which is very low down here and its immediate neighbor is very high up here, because this estimate here would jump through that object. So what if we assume that all neighboring objects are the highest they can be? So in order to do this, I'm going to remove this looping code, and we're going to bring back this basic definition. And I'm going to take the width, or the height, is going to be equal to sine of I time again, plus center. And if I put that in here, we get our original code where each object has its own height. Actually, I have to multiply this by 2, so we got more extreme variance. So the way we can do this is by asking, or explicitly getting, the closest neighbor. So if my point is here, and I'm in this cell, the closest neighbor is in this direction. And then if I'm on this side, the closest neighbor is in this direction. So what we can do is we can define a new float variable down here called neighbor, which is the neighbor of the center for point P. So in order to get the neighbor, we have to offset center by -1 if the point is on the left side of the cell, and by +1 if it's on the right side of the cell. So what we do is we take center, and we add and we're going to have to use the ternary operator here. We say if p.x is less than center, meaning it's on the left side, we have to return -1 or subtract -1. And if it's on the other side, which is on the right side, we have to return 1. So next we have to do some slight refactoring because we need to keep p to be the same value as was passed in. So we can't take the fractional component here. So instead what we're going to do is, because we have the center point of the current cell, we can just map p to that point by subtracting it by that. So when I run this, it should be the same. So here I'm basically saying, give me a piston that is centered at the point at that midpoint of the cell with the width and height. So this is the piston for the current cell. Now we're going to get the worst possible piston for the neighbor. So I'm going to call this me, which is my cell. And then we're going to call next to be the neighbor cell. And what we do is we just take this here, and instead of subtracting by the centroid of the current cell, we subtract by the neighbor of, or the centroid of the neighboring cell, which is going to be this. And then also, instead of passing in this varying height, we pass in the worst possible height, which in this case is 2. So when I run this, I need to return a value first. I need to return the minimum of me and next. So we're taking the union of these two objects. Me and next. Semicolon, run. So now the SDF looks pretty weird because we've got these weird artifacts from what we've just done. And I'm going to argue that these artifacts, although they make it so the sine distance function underestimates the distance, it will always make it so it never overestimates the distance. So I can't put my cursor anywhere and have this circle intersect with the object. And that's good for array marching because if we overestimate an object's distance, we can jump through it. But if we underestimate, it'll just take longer to get there, but we'll still get there. So this essentially allows these pistons, this piston SDF, to be glitchless when we actually render it, but require no loops whatsoever inside of the SDF function. And this method can be abstracted or generalized to higher dimensions, which I'll show in a minute. However, first I need to talk about some caveats here. First of all, it's because the sine distance function underestimates in some places, array marching will take longer, and depending on the complexity of your scene, this could cause some issues where you run out of loop iterations in your array marching loop. The other issue is that because the sine distance function underestimates in some places, certain lighting tricks like fake ambient occlusion or fake soft shadows might have artifacting where it encounters some of these underestimated areas. Okay, now let's generalize this to a 2D grid of pistons in 3 dimensions. So now we're in 3 dimensions. I'm going to quickly show what this code is like. We've got our array marcher down here. There's some code so we can do mouse rotations, so I can look around this object. I've got some metallic-like material applied to our object. And our object itself is essentially the piston 2D sine distance function, which we defined in the previous shader, except it's been rotated around the z-axis. So the z-axis is the up axis, and the x and y axes are the floor axes. So first thing we're going to do is domain repetition along the x and y axes. And to do that, we're going to get the centroid of each domain, and then just subtract p by that centroid. So now we have domain repetition by getting the center point of each domain, and subtracting p by that center point. So next we're going to have to figure out, for each point in the domain, given p, what is the closest neighbor domain? So in order to answer the question of what the closest neighbor is for a given domain, we have to use this function called edge. And it's a little complicated, so I'm going to jump into a graphics editing program to help explain what this function is doing. So what we have here is a box censored at the origin, and we have a point inside of it. It can also go outside or anywhere really. And what we want to do is we want to get a vector, so I'm going to draw an arrow, a vector from the origin to the closest edge. So let me give a pointer here. So for this point, we would get this arrow If the point was more over here, we would get this arrow. And so in order to compute this, what we first do is, suppose the point is down here. First, we take the absolute value of its coordinates, and that will have the effect of mirroring it across these two different axes. So this is duplicated as a variable, and I think if I take the absolute value, it'll be here and then here, I think. So I'm just going to color it red so that we know it's not actually the point. So that maps it up here into this quadrant. And because it's up in this quadrant, our math can be simpler. And what we do is we ask, okay, is this point, and I'm going to draw another line and make this dashed. So we ask, is this point on the top or bottom side of this line? And if it's on the top of this line, we get the sine of the y coordinate, and that will help us get the vector. And if it's on this side, we take the sine of the x coordinate, and that'll help us get that vector. And we basically take the sine of the x coordinate, put it into the x coordinate of the return variable, and the other coordinate will be 0. And if it's on this side, we take the sine of the y coordinate, put it into the y coordinate of the return vector, and set the other coordinate to be 0. So with that explained, the way we use edge is quite simple, really. So what we do is we need to figure out what the neighbor is for the center. So we take neighbor to be equal to the center plus the edge of p dot xy minus center. So what edge is doing is saying, given the current point, which edge of the box centered at center is closest to P. And then we add that to center to do the offset. So if I run this, hopefully it'll build. Yes, it works. So now what we can do is start moving these pistons independently. So now we have to change the height based on the center position. So I'm just going to take like sine of center dot y plus sine of center dot x, or rather center dot x, and then multiply that by 2. And hopefully that gets us a pattern. And let's add I time to this. You can see it's extremely glitchy because we're not doing our trick of assuming the worst. Like in the previous example, we define me to be equal to the current piston. And then we define the next piston, or the neighbor piston, to be just the piston centered at the neighbor. And the height is going to be the maximum height, which is going to be 2 in this case. And then we return the minimum of me and next. And if I did my math right, this should work. So this almost worked. Unfortunately, there are some glitches still. And it turns out I had a typo in my edge function. This should be a greater than instead of a less than. So let's run this. And now there are no more glitches, and the pistons are interacting correctly, and we don't have any overshoot or anything like that. So yeah, that's the two-dimensional case, or the two-dimensional array of pistons. But now, how do we go one step further? What if we had an object that is repeated in 3 dimensions, and what if we want that object to be different in each domain? So I'm going to go another dimension higher, and I'm going to show you how to do that. Okay, so now we have a different 3-dimensional scene. This one has a box, which is quite a bit longer than it is wide or tall. And the code down here is in Sine. And what we're going to do is a little bit different than the other pistons examples. We're going to have a bunch of these repeated in space, and each domain is going to have a different rotation for this box. So in order to do the 3-domain repetition is we define the center for each domain, and that's going to be the floor of P plus 0.5. I cannot type. And in order to do domain repetition, we just need to subtract P by center. So now we have all these boxes repeated. And now what we can do is rotate each one by a different rotation. So I've defined this hash function up here to let us pick a random rotation value for each cell. So over here, I'm going to say HS, which stands for our hash value. It's going to do the hash of center.x and center.y. And we hash that with the z value as well. Okay, and this hash value ranges from -1 to 1, so we need to multiply it by some large value to get the full range of rotation. And so let's just run that, make sure it compiles. So we want to rotate this whole vector. So we're going to save that down here. So we're going to say vec3 position is equal to this. And then position is going to be equal to erot position vec3. And we're going to rotate it around the z-axis. And hs times 100 to get the full range of rotations. So this erot function is a function which is defined up here. This is a very useful function that I think everyone should memorize. It is a function which allows you to rotate a point by an arbitrary axis by a certain amount of rotation. And in the description, I'm going to link a full description of this function and how it works, so you can use it in your own projects. So if I now pass position into box again, each square will have its own rotation. So we are already seeing a lot of glitches. So we're jumping through objects all over the place. And that's because, like I said before, each object assumes that its neighbor is the same object. So what does it mean to assume the worst in this case? Because unlike the piston case, where we have these very well-defined notion of a height, what is the worst case scenario in this case? The worst case scenario is pick a rotation that the neighbor could be in that will cause an overshoot. And so what we could do is we can say, like, okay, what if we take the union of all possible rotations? And that would create a disk centered at the same place. So I wonder if I can visualize this for you. So let's get rid of the domain repetition and just have the position. So let's comment that out. Oh yeah, we don't have HS. So let's just put in I time here. So we have this, this is the object which is being repeated across all the domains. And the question is, how do we take the union of every single possible rotation? And so the way we could possibly do that is through a surface of revolution. Okay, so I've written a bit of code here without talking, but essentially what I've written is a representation of the union of every single possible rotation of that box. So you can imagine that box sweeping out this arc that defines this sort of convex hull, you might imagine it. So this is the convex hull of that object. So now, when we get the neighbor position, we can return this worst SDF, and that should get rid of our glitches. So let's bring back our domain repetition. So in order to answer the question of what the closest neighbor is for a given domain, in 3 dimensions, it's slightly more complicated than the 2-dimensional case, but it works on the same principle. So in the 2-dimensional case, we imagined a point inside of a box centered at the origin, and we wanted to know what is the closest edge to that point of the box. And in the 3-dimensional case, it's basically the same thing, but instead we want to know what the closest face is for a point in the box. And so in order to get the neighbor, we just take vec3 of neighbor is equal to center plus face of p minus center. So that's our neighbor. That's the center of our neighbor cell. So we run that. And what we could do is take vec3 of, we can define a new vector, and we take, subtract that by neighbor. And that's the same thing as we're doing here. And we pass that into our worst SDF. And then we are still returning the SDF for each individual cell, so we have to take the union of this and this. So we're going to say float of me is equal to this, and we turn min of me and worst. So now there are no more glitches. So hopefully this gives you a principled way to fix these kind of glitches when you have repeated domains, where each domain is slightly different. And the solution, and as I was working on this tutorial, it sort of came to me. For a given domain, you have to find the neighbor for the current point, the closest neighbor domain, and then put at that domain the worst possible object, which will be the convex hull of the SDF. And then you take the minimum of that object and the current object for the current cell, and that should get rid of all glitches. Yeah, so hopefully that helped somebody. I hope you enjoyed this tutorial. Like, share, and subscribe. I don't know, but have a good day, everybody. Goodbye.